Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comstate University, Islamabad campus. The topics that I'm going to discuss in this lecture are interfacing input and output devices with 8086 microprocessor and interfacing input and output devices with 8088 microprocessors. The slides that have been used in this lecture are edited from the two sources given here. So in 8086 working in the minimum mode, this is the block diagram of microprocessor when it is working in the minimum mode and connected to the external world. So the microprocessor here is taking input clock signal from a clock generator, and it is connected with the external environment, RAM, ROM, and input and output devices. After the signals coming from the microprocessor are demultiplexed and buffered. So this is additional circuitry that is used to demultiplex multiplexed fins and to buffer some of the fins which are not demultiplexed. So it is the 8086 microprocessor connected with input and output devices, ROM, RAM, and other circuits. When 8086 microprocessor is working in the maximum mode, some of the control signals are generated through a bus controller, 8288 bus controller. While these signals are generated by the microprocessor in itself when the 8086 microprocessor is working in the minimum mode. And this is how 8086 microprocessor look when it is operating in the maximum mode and connected with the input and output devices here, ROM, RAM, and other circuitry used to demultiplex and buffer buses. There are two types of input and output devices are addressing. The input and output system allows additional peripheral devices to provide data or receive results of processing the data using input and output ports. So the computer system, the microprocessor, is operating on the data, and the results are shared with external environment through these input and output devices, which are connected to the microprocessor through the input and output ports. The 8088 and 8086 microprocessor imply normally two types of input and output interfacing. One is called isolated I/O, and the other is called memory mapped input and output. The difference between the two is in the sense that how input and output ports are mapped into the address space. So the microprocessor has a range of addresses, possible addresses. So so how those addresses are mapped into input and output devices. In that aspect, there are two types of input and output. One is isolated I/O and the other is memory mapped I/O. In isolated I/O, there are special instructions for input and output operations, the in and s, out and out s. So the s represent the string instruction. So just like the data transfer instructions, move s and move, and there are two variants of input and output instructions. One is n and the other is ns, that means to bring string data inside, and out s. Transfer these instructions transfer data between the microprocessor's accumulator register or memory and between input and output devices. So it transfer data from accumulator to input and output devices, or from memory and input and output devices. In the memory mapped, the input and output instructions are not used, but any instruction, any assembly language instruction that reference memory can accomplish the transfer. So in the isolated, there are special input and output instructions responsible to move in and out data from the microprocessor and from the input and output devices. While in the memory mapped, any instruction that reference memory can do the memory input and output transfer. The personal computers doesn't use memory mapped I/O. They're using only isolated input and output technique. Obviously, there are some advantages of isolated input and output. In isolated input and output, the complete 1 megabyte memory address space is available for use with memory. In 8086 and 8088 microprocessor, the total memory that can be connected is or interfaced is 1 megabyte memory, and the total memory addresses are 1 mega addresses because there are 20-bit address. So the 20-bit address is sufficient to address 2 raised to the power 20 or 1 mega locations. So this total capacity can be used for the memory, and also special instructions have been provided to perform input and output operations with maximized performance. There are some disadvantages of isolated I/O as well. All input and output data transfer must take place between the accumulator register and the input and output port. So the special input and output instructions N and S, out and out S, are using the accumulator inside the microprocessor to send or receive the data from. So this is a kind of disadvantage. Data transfer between I/O and the microprocessor must be accessed by these 4 instructions only. So there are not too many choices to send or receive data from the input and output I/O input and output devices. Here we have a set of input and output instructions. On the left column, we have the instruction. This is the data width, that is the size of the data that it can transfer. And here is a brief explanation of each instruction. So NAL-P8, so this P8 is an 8-bit port, immediate port, and this is this instruction reads a byte of data into the accumulator AL from the input and output port P8. This P8 is an 8-bit port address, and that is provided as an immediate value in this instruction. So when NAL, P8 is used, this instruction reads an 8-bit data from the input and output device connected to the port addressed by this 8-bit address, and that 8-bit data is read into accumulator. So 8-bit data is read here, while here in this instruction 16-bit data is read from this 8-bit port. So this port is an input and output device is connected with this port, and the address of this port is an 8-bit address, and this 8-bit address designate an I/O, and then 16-bit data is read from that I/O into this accumulator. And similarly here 32-bit data is read, while here these instructions are called fixed I/O, while these instructions are normally called variable I/O. So here the address, the port address, or the address of the input and output port is provided through a register DX. So this is always DX register. So this instruction reads 8-bit data from the port addressed by the value here in this DX register, and this 8-bit data is read into accumulator AL. And here 16-bit data is read from the port addressed by DX into AX, and the amount of that data that is being read is determined from the size of the destination register here. So AL is 8-bit, X is 16-bit, it is 32-bit, so that's why 8, 16 and 32-bit is the data that is being read by these instructions. Here we have some string variants of string input instruction. NSB is a string instruction, so it reads data, string data, byte string data. So this instruction reads a byte is input from the port addressed by DX register, and that byte is stored into the extra segment memory location addressed by DI. So here the data is read and stored inside the memory, and the memory is the target. So the target is normally the extra segment, and the offset for the extra segment when string instruction is used is provided by the destination index register. And the source here is the input and output port, and the address of that is implicitly provided through the DX register. Similarly here, the port address is stored in the DX, so the 16-bit data is read from input and output device addressed by the address in DX register, and their data is stored in the extra segment memory location addressed by the destination index, and here 4 bytes of data is read. These are the output variant of the input instruction. So these instructions send data from the accumulator to the input and output device. So here AL is the accumulator, so 8-bit data from the accumulator is sent out to the input and output device with address P8. So P8 is an 8-bit port address. And here 16-bit data from the accumulator X is sent to input and output device P8, and here 32-bit, and here the variable port addressing is used, where the accumulator is sent to input and output device addressed by DX register. And these are the string variant of out instruction. So this instruction is sending data outside to the input and output device. So this instruction is sending a single byte of data from the obviously the source is the data segment, the memory segment is the source, so that is normally the data segment. So this instruction is sending 1 byte of string data from the data segment memory location addressed by source index register, and this single byte of data is sent to the input and output device with port address stored in the DX register. So DX register is not shown here, just like it was not shown here, but this DX register implicitly provides the input and output port address. Similarly, the other two instructions send 16-bit and 32-bit data from the data segment memory location addressed by source index register, and the data is sent to input ports designated by the register DX. And isolated input and output in 8086 and 8088 microprocessor. Here we have the memory address space. So in case of isolated, this is a total memory, 1 megabyte memory with starting address from 0000 till FFF. So all of these memory addresses, which are 1 mega addresses, so all of these addresses are used for the storing the memory, storing the data in the memory. While for the input and output addresses, there is an additional there are additional 64 kilo addresses. So those addresses are 16-bit addresses represented with as 00 till FF. Here we have this 10 is incorrect, so this should not be here. So this is 4 zeros, 301, and then FFF. So these are 16-bit addresses, and the total input and output address space is 2 raised to power 16. So this address space is separate from memory addresses. So for the memory, there are 1 mega addresses, and for the input and output, there are 64 kilo addresses. So by isolated, we mean that the memory addresses are isolated from the input and output addresses. Memory mapped I/O doesn't use the N and S and out and out S instructions. So microprocessor looks at the input and output port as though it is a storage location in the memory. So whenever the microprocessor is accessing an input and output port in the memory mapped input and output mechanism, then the microprocessor thinks that the memory is being accessed because the instructions are the same memory referencing instructions, but unlike the other memory referencing, in this case some of the addresses are used to access an input and output port instead of accessing a memory. But to the microprocessor, it appears if it is accessing the memory, but practically the microprocessor is accessing the input and output device. So some of the memory address space is dedicated to input and output ports. Instructions that affect data in memory are used instead of the special I/O instructions. So those special 4 instructions are not used in the memory map, and instead all other instructions that are referencing memory may be used for the input and output. So this would give us more instructions, and addressing modes are available to perform I/O operations, because normal data transfer instructions are used for I/O, so more instructions and addressing modes are available. I/O transfers can take place between I/O port and other internal registers, because those other data transfer instructions can access other internal registers as well, apart from accumulator. So other registers, the data can be moved between input and output port and other internal registers of the microprocessor. The memory instructions tend to execute slower than those specially designed for isolated I/O. So these instructions are much faster. Advantages: any memory transfer instruction can access the I/O device. So this is an advantage. And disadvantage is that a portion of the memory system is used as the input and output map. So this reduces the total memory that can be interfaced with the microprocessor. The total capacity of memory is reduced, as shown here. So this is in case of 8086 and 8088 microprocessor, where we have a total of 1 megabyte of memory. 1 mega are the total number of locations. Address or memory address space, that is the total memory address space. So out of this total memory address space, some addresses outside of this memory address space are reserved for the input and output devices. So these addresses here are then the addresses of the input and output ports. So these are not the memory location addresses, but they are the addresses of input and output ports. So whenever the microprocessor is accessing, for example, this location, then the microprocessor is accessing a memory location. But when the microprocessor is accessing this location, to the microprocessor it looks as if the microprocessor is accessing this location, but in reality the microprocessor would access port 0 and port 1, which is port 0 in 16-bit port mode. So each port has 8-bit address, but this 8-bit part and this 8-bit part met together represent a single 16-bit port. So these are the address space taken from the memory space. So these memory addresses cannot be used for storing the data in storing the data in the memory, because these addresses are used for the input and output ports. Here we have some reserved ports used in the personal computer normally. So these are all these ports are used for reserved for the computer system and the ISA bus. And out of these ports, some of the ports are fixed port I/O instructions are used. Fixed port I/O instructions are used because they are using 8-bit fixed port number as an immediate port address, as we saw some example with P8 in the previous slides. While the input and output ports from here and onwards, they are variable port input and output instructions, because these port addresses are 16-bit, so they can only be provided through the DX register, while port addresses still here are 8-bit ports, so they can directly be provided. So that's why they are called fixed port I/O instructions, while here the port addresses are 16-bit or more than 8-bit, so that's why these port addresses would be provided through the DX register, and that's why they are called variable port I/O instructions. So instructions, port addresses from about this point are used for PCI bus. They can be used by the user applications and the mainboard functions. This is a very simple example of how a basic input and this basic input interface can be created. So in this circuit, it's here we have 8-bit toggle switches, and these toggle switches can be switched on and off. These toggle switches are connected with ground, and external source VCC is provided through registers here. So these toggle switches can be the source of data, 8-bit data. So assume that this together is an 8-bit source, and as this is an 8-bit source of data. So and it can be enabled or disabled through this circuit here. So 1G and 2G are the select lines. So this is a circuit, and this circuit simply puts the value or the bits provided here onto the data bus whenever both of these select lines are zeros. So this complete circuit represent or can be considered as an input device that provides input 8-bit input data to the data bus. So whenever an I/O port address is sent by the microprocessor, that I/O port address is at the end decoded to create a control signal, and that control signal is called select, and that select is connected to 1G and 2G select or enable inputs of this chip. So whenever this 0 is provided here, it would enable this chip that would just pass on the input data here created by the toggle switches to the data bus. So data bus, so the microprocessor would read the 8-bit data from this device. So whenever the microprocessor is executing an 8-bit an input instruction reading 8-bit data from the input device, then that instruction would create an address, input and output port address, that would be decoded to send a 0 at this select line, and this would enable this circuit and would be able to put the 8-bit value here onto the data bus, and that would be read by the microprocessor. So this is a simple example of how to create an input device to provide 8-bit data to the microprocessor. While here in this example, a basic output interface is created, and whenever here we have a circuit which is connected with VCC, then with every line we have a resistor and light emitting diode is used here on each line. So whenever the microprocessor is providing the data, which is the microprocessor intends to send it to an input and output device, then at that time microprocessor is also creating an input and output port address, and that port address would serve as the clock signal to this device, which is actually a set of D flip-flops. And these D flip-flops would not provide the input data here onto the output lines until the select line is 0 here. So whenever the microprocessor is executing an out instruction that is sending 8-bit data to an input and output port, this select line is 1, but when that instruction is being executed, the instruction would generate an input and output address, and that address would be then decoded by the microprocessor circuitry, external circuitry, to choose this line as 0, and this would serve as the clock signal for this for these D flip-flops, and these D flip-flops would then be able to pass on the 8-bit data from provided here to here, and when this 8-bit value is provided here, this would light the light emitting diode, and this is a kind of output device. So the data is coming from the microprocessor, and the data is being sent to this output device using an output instruction. So this is a simple block diagram of how 8088 microprocessor in the minimum mode can be connected to with a number of input and output devices. So here we have input and output control signals here, the multiplexed and the multiplex data and address buses here, and other address buses here, and some control signals are here. So all these signals, data, address, and control signals are connected with input and output interface circuitry, and this circuitry may be composed of some decoders here. And with this circuitry, there are a number of input and output devices are connected with this circuitry. And a similar block diagram is shown here for the 8086 microprocessor, which is working in the minimum mode. So here again, there is an input and output interface circuitry. Input and output devices are connected with this input and output circuitry. And from the microprocessor, a number of signals are coming to and from this circuitry. So here the multiplexed address and data bus is coming here from the microprocessor till the circuitry, and there are other control signals as well. In case of the maximum mode, when the 8088 microprocessor is working in the maximum mode, the control signals are generated by the bus controller. So the status signal S0 till S2 are coming from the microprocessor to the bus controller, and then this bus controller is generating a number of specialized input and output control signals. So these control signals are connected to the input and output interface circuitry, and in a similar fashion, input and output devices are connected with the circuitry here. And if the 8086 microprocessor is working in the maximum mode, again the same controller is used to generate the control signal. And a minor difference is that the multiplex pins or the multiplex bus is now 16-bit, because the 8086 microprocessor is having 16 pins are multiplexed for data and address, and the rest of circuitry is almost similar. Okay, so here we have a simple decoder where an 8-bit IO port address is decoded here. So this circuit is called 74LS138 decoder. This is a 3 to 8 lines decoder. Whenever an input is provided here, only one of the output is 0, while all of the other outputs are 1. So let's assume that the microprocessor is sending an 8-bit address, and this 8-bit address is in this example is the 8-bit address is providing the address of 8 input and output devices. So and there are 8 input and output devices are connected, and each the select line or the enable line of each input and output device is connected to one of these 8 lines. For example, device 1 is connected to this line, device 2 is connected to this, device 3 is connected to this, and so on. Or maybe numbering start from 0, so device 0, device 1, device 2, and until device 7. So 8 devices are connected to this decoder here, and when an 8-bit address arrives, 3 of this 8-bit address are connected to the select lines of this decoder. So these values A0, A1, A2 would select one of the outputs to 0, and the other outputs would be 1 at that time. While the rest of 5 bits of this 8-bit address are connected as this. F4 is connected with G1, F5 and S6 and S7 are connected to G2B through a multi-input NAND gate, and A3 is connected to G2A. So to enable this decoder, G2B and G2A must be 0 here, so 0 should be provided here, while G1 must be 1, otherwise this decoder will be disabled. So to enable this decoder, we need 0 here, we need 0 here. So to get 0 here, S5, S6, S7 must be 1, so that we get 0 here. And to get 1 here, F4 must be 1. And to get 0 here, A3 must be 0. So F4, F5, S6 and S7 must be 0, and A3 must be 1. So whenever either of these input and output devices is to be addressed, then the most significant 4 bits must always be 1. F4, F5, S6 and S7 must always be 1, while A3 must be 0. So the most significant bit, 4 bit, are 1, while the next bit on the right is 0. Only these 3 bits are changing. So if all of these are 0, so here we have 4 ones on the most significant bit, so that's why we are having 1 F here, and for the first address these 3 values are 0, and these 3 bits are 0, and A3 is always 0, so we would get 0 here, so 0 hexadecimal digit. For the next address F1, F1, for the next address F2, F3, and finally F7. So these are the possible 8 valid input and output addresses, and these addresses are decoded by this 3 to 8 lines decoder, and each time an address is sent, one of these addresses is sent, these addresses would select either of these input and output devices. Even though 8-bit address is sufficient to provide 2 raised to power 8 or 256 total input and output addresses, but in this simple example only 8 input and output addresses are used. Okay, so here are some simple example of writing programs, input and output instructions to manipulate input and output devices. So, okay, in this example, write a sequence of instructions that will output the data FF16. That means FF is a value in hexadecimal. This is an 8-bit value to a byte-wide output port address. This is a fixed port. B is an 8-bit port address, and this is the data that we want to send it out to this device. So to write instructions, first the value that is to be sent, that is to be stored in the L register. So the L register is loaded with FF as an immediate operand in the instructions. So to first, this value is stored in the accumulator L, so move L 0FFH. So this 8-bit value which is to be sent to the output device is first stored in AL register, and then out 0ABH AL instruction is used to send the 8-bit value here to the output device. This one, this is the 8-bit port address of the output device to receive this 8-bit value from AL. So this is actually P8, which is a fixed 8-bit port address. Okay, so another example, write a series of instructions that will output FF16 to an output port located at address B0000616 of the IO address space. So write a series of instructions that will output. So this is the value that is to be sent output to an output port located at address. So this is the 16-bit address of the input and output device to receive this 8-bit value. Okay, so as this is a 16-bit port address, so this cannot be provided as a fixed instruction. So for that, variable input and output port instructions are used, and in those instructions, the DX register is used to store the output port address. So this is the output port address. This is first moved to the DX register, as this DX register always stores the output or input instruction, the input and output port address. So first the output port address is first loaded into DX register, and then the value to be sent out is FF, that is also stored in the accumulator AL. As this is an 8-bit value, so that's why it's stored in the accumulator AL. If it is a 16-bit value, then this would be stored in X register. Okay, so then out DXL, this instruction would send the 8-bit value in accumulator L to the output device with port address designated by the DX register. Okay, so here the data to be read from the 2-byte wide input ports. So an input port which is the address of which is 2-byte. So the input port has the address of a 16-bit or 2-byte wide input port. An address AA and N916. So these are the two values, two addresses, in fact, 8-bit addresses in hexadecimal, and then output as a word wide output port. So what this example says that 2 bytes data is read from these two ports. So this is an 8-bit port, this is an 8-bit port. So 1 byte is read from this input port, and the other byte is read from this input port, and then these 2 bytes are written outside to this output port. So to do this, first read in byte at address AA16. So from this input port, the single byte is read from this input port into accumulator L. So to do that, this is the input fixed address, input port fixed address. So NAL0AH is used. So this is the input port address, and from this 8-bit input port address, 1 byte of data is read to accumulator AL, and then this data is pushed to the upper place of the register H, because we need to use L for the next byte. So that's why this byte is pushed to the H part. So that's why it is moved from L to H. Now we can reuse L. Now the other byte from the other device, which is 09A, this is the other input port. So from this input port, another byte is read to L. So now we have the first byte read is in AH register and the other byte rate is in AL. So AX register now maintains that 16-bit value. And now the second part of the question is to send that 16-bit value to the output port, and the output port is now first moved into the DX register. So 16-bit port is now moved to the DX register. Now DX register has the address of output port, and now this instruction out DXX is used. So this instruction is sending the 16-bit value in X register to the output port addressed by the value in the DX register. So these are simple examples of how input and output instructions may be used to send and receive data from the input and output devices. So all these instructions are using input and out, and even if they were using NS and out S, these instructions mean that the microprocessor is working in the isolated mode. If it would be working in the memory mapped I/O type, then any other instructions working using for the data transfer like move and other instructions would also be used for the input and output transfer. But most commonly, normally the isolated I/O type is used for the data transfer into input and output devices, and these are the instructions. In and out instructions are used to send and receive data from the input and output devices. And we also studied some simple example of how the input and output addresses are decoded so that input and output devices may be located or identified, just like the memory interfacing. Thank you.